So here we go for an example of a real-world example.
We better put on our thinking caps and think hard.
Okay, we got a 4-foot-long spring that measures 8 feet after an 8-pound of weight's attached to it. By the way, that's not much of a spring, is it? It sounds like it's already sprung. Anyway, the medium in which it moves offers resistance numerically equal to the square root of 2 times the instantaneous velocity. So find the equation of motion if the weight is released from equilibrium position with a downward velocity of 5 feet per second. Find the time in which the weight attains extreme displacement from the equilibrium position. So, first of all, mass times gravity is weight. So 8 over 32 equals 1/4. We said it was 8-pound weight. There's gravity, so mass is 1/4. F of x equals kx, so when it's displaced 8 feet, that's proportional to the 4 feet that it was moved. So 8 pounds extends from 4 to 8 feet. So k equals 2. Our equation so far is 1/4 second derivative plus square root of 2 times the first derivative plus 2 times y equals 0, with initial condition y is 0, so it was at rest originally, but it was given an impetus downward of 5 feet per second. So, messy looking equation, multiply both sides by 4 to solve this homogeneous equation. Characteristic equation, m squared plus 4 square roots of 2m plus 8 equals 0, which has m equals negative 2 square roots of 2 as its double root. So our solution of the homogeneous equation would be c1 e to the negative 2 square roots of 2t plus c2 times t times e to the negative square roots of 2t. So that's the general solution. Since y is 0, then we know that c1 equals 0. And since y prime, which is, oh, this is complicated, negative 2 square roots of 2c1 times e to the negative 2 square roots of 2t plus c2, remember we've got to take a derivative of this term, so first d second, actually I have second d first. Here's second, here's the derivative of c2t plus second d first, or first d second, this is first d second, or really, if you simplified all that, you get c2 e to the negative 2 square roots of 2t minus 2 square roots of 2 c2t e to the negative 2 square roots of 2t. Notice that since c1 was 0, we didn't bother to put that one in here. So c1 0, so we got y prime of 0 equals 5, and that forces, this is all going to go to 0, that forces c2 to be 5, and the solution is y equals 5t e to the negative 2 square root of 2t. So extreme displacement occurs when y prime, the velocity, equals 0. Think about it. You got a spring bouncing up and down. When is it going to be at its further point? The answer is when it's temporarily stopped at the end of its displacement. So, setting y prime to 0, this is our y prime here, so set that to 0 and solve it. You would get 1 minus 2 square roots of 2t equals 0, so t equals 1 divided by 2 square roots. By the way, of course, you get times e to the whatever, but that's divided out by that. That's never going to be 0. And the c2 we already know to be negative 5, and we could divide out by that, so we get 1 minus 2 square roots of 2t equals 0, so t equals 1 divided by 2 square roots of 2, simplifying to square root of 2 over 4 seconds. So that's the time in which it has its maximum, that is, its extreme displacement.
Oh, I see.